Hello, if you have been following along, this is the second video in a three-part series about chaos animation. In this series, we are exploring the math and programming behind animating chaotic systems. In this video, we'll discuss the famous Lorenz system in particular. In 1961, an American mathematician and meteorologist, Edward N. Lorenz, wanted to create a simplified model to capture the essential dynamics of atmospheric convection. He wanted it to be basic enough to perform useful analysis with the computers available at the time. 2 years later, while running a simulation of his system on the computer, Lorenz steps out to get a cup of coffee. When he returns, he discovers something astonishing. Inputting two nearly identical initial conditions resulted in vastly different outcomes over time. He would later coin the popular term the butterfly effect when he wrote that a butterfly flapping its wings in Brazil could potentially influence the weather in Texas. But why should we study the Lorenz system? Not only is it used as a simplified model for atmospheric convection, but it serves as a starting point for more complex fluid systems in engineering. Most importantly, however, is its sensitivity to initial conditions, making it the quintessential chaotic system which we seek to animate. The Lorenz system is described by the following three ordinary differential equations, ODE for short. This means that the values are changing with respect to time. Let's begin by rearranging the equation to model changes in x, y, and z respectively. We can set some initial conditions as shown. Sigma, beta, and rho are the constants we wish to define. dt represents the time elapsed between iterations, which we can set to 0.01. Now, for an initial x, y, and z, given the defined constants sigma, rho, beta, and dt, we can calculate dx, dy, and dz. These changes will be added to the original values. This is known as the forward Euler method, and we just developed a numerical technique for solving ordinary differential equations. After storing values of x, y, and z for multiple iterations, we can get a beautiful butterfly-like graph as shown. You can animate this graph by plotting points after each iteration. The following goes through about 600. Thank you for making it to the end of the video. All graphs and animations used in this video were generated in Python. I've linked the source code in the description for those of you who are interested. That being said, please like and share this video. Subscribe if you enjoy and would like to see more of this type of content. Goodbye.